element, what I'm really trying to tell it to do is distribute that force on two nodes or on how many ever nodes are lit on that particular edge. And so there's some calculations that are going on behind the scene that changes that. But the solver expects the loads to be on the nodes themselves. And nodes are where the boundary conditions are also applied. So if you're going to make this a cantilever type problem, you would fix the nodes that end up being at the wall. You would fix them so they could not move in X, Y, or Z. So nodes are just a bunch of points populated out in the space. If we wanted to kind of look at the 1D nodes, they are locations along, say, the x-axis. They are used whenever doing kind of rod type elements. So if you're just trying to approximate this cantilever beam by a simple rod where you specify the cross-section of what the rod is, you can represent it just by x values representing the nodes. An x value of 0, an x value of 1, an x value of 2, an x value of 3. You could break it up into a rod that had a number of nodes along it. 2D nodes have both x and y values, and 3D nodes have x, y, and z values. So anytime you're doing kind of a cross-sectional analysis, you're typically going to be using 2D nodes. Whenever you're doing a 3D free-form shape, you're going to be using 3D elements. Now we need to talk a little bit about elements. Elements are the logical connection of a set of nodes. An element can be a first-order element, which means every node is connected to an adjoining node by a rod. Okay. If we were to talk about a second-order element, we would find out that a second-order rod has 3 nodes on it, and that rod could actually approximate some kind of quadratic curve. So if you were trying to do a bent cantilever pipe and you knew it was going to bend in a certain way, you could do that. If you were doing an area analysis, you could have your rectangular element basically have midpoints on each edge, and that would be a second order element. They also have cubic elements, and cubic elements will have, on a rod, would have 4 nodes that could make it approximate a shape like that. So just from that little discussion of nodes and elements, if you want to get an accurate result and you wanted to go linear, what are you thinking, what would your thought process be on trying to get accuracy into it? First order, you're going to use a first order element. You're going to want the element size to be small. If you're going to go to a second order or third order element, you can begin thinking about larger elements, which generally is going to compute the fastest. First order, but if you get up to really high number of elements, it still may take a long time to process. And so there's a trade-off between the order of element and the speed and the accuracy. So that's kind of the issue that you're going to be thinking about as you do your finite element. Yes?
Is it normal to maybe have a preliminary analysis using first order and then
Yeah, in fact, you'll find out in industry whenever they're doing kind of conceptual design work or even preliminary design work, it's generally always first order. They're just blasting out elements, and the elements are usually pretty crude, pretty rough as far as their length or edge length. But as they get closer into the detailed design phase or to the final production phase, you will see them just ratchet up the node count, the element count, and begin switching to higher order elements at the same time to get a better accuracy. So for doing the shape function, for developing kind of the single representation of how an element behaves, okay, there's kind of 4 different approaches that you can use to kind of come up with that general formulation. The first one is a direct method. The direct method kind of goes back to your strength of material. It's, you kind of look at it, observe it. It's a fairly straight up, it's based on physical reasoning and things like that. The next 3, the variational, the weighted, residual, and the energy method, are the ones that basis for modern finite element solvers. In the 501 class here at BYU, they really don't talk about mathematics behind those. In the 506, they will spend a significant amount of time developing the mathematics for the variational, the mathematics for the weighted residual, and the mathematics for the energy method. In the book, I think the author does a reasonable job of kind of describing the differences of these methods and their approaches. In this class, we basically allow the CAD system to produce its formulation. And the formulation that we use is tied directly to the element that we choose. So when you go into the CAD system and say, I want a quad element or I want a tetrahedral element, as you're choosing those elements, they have a method already kind of associated with them. Just to understand a little bit of the mathematics, if we're calculating just the node points, okay, if that's all we're calculating, how does the CAD system provide a nice shaded model? It would be very blocky in its results. All of us have seen some kind of finite element results, and it's usually a very nice gradation across the model, showing different levels of stress. Well, how they do that is basically through interpolation. And it's using the corner points where all of the action, the loads, the deflection, everything is being calculated. And it's basically using that to then interpolate any point inside of the element, inside of that 2D or 3D element. So if we have a rod, as a simple example, and we wanted to divide it into 2 elements, we would need 3 nodes to do that. On the 3 nodes, we could basically discretize that or break that into element 1, having node 1 and 2, element 2 having also a node 1 and a node 2. Okay? So these are kind of the local view of each element. So that's the way we would kind of discretize it. We would break it into its formulation. So here is the spring times the deflection equals the residual, the stress, or the force. Do the same for the second element. So in the discretization process, the CAD system comes up and represents the problem if we're just doing a bar in these simple little formulations. What they have to do is then kind of merge them together into a global matrix. And so you'll notice that all of a sudden they're combining the individual matrices and they're adding K22 to K11 from the second element. Those get added together. And we get the stress of these elements basically joined together. And we do the same thing for the R's, for the forces on this thing. So that's our global matrix and kind of the numbering that happens. You can think how complex this would become if it were a 3D element and there were 10 million of them that you had to put together. So it starts literally building this very gigantic matrix. The next thing that you have to do is you have to then begin to put in the boundary conditions. So the boundary conditions say stress at 1, stress at M is equal to 0. And so we drop out some of those terms, okay? So we lose the top row, we lose the M row in this thing because there's 0. We have to then apply the loads, which are the known forces acting on this thing. So those get plugged into the R values. And once those are plugged in, then we have to solve this problem. Is it an easy problem to solve? We blew away a few equations, and so we actually have kind of an over-constrained. It's going to be too many equations, but the computer can go through and solve that very quickly just by taking the inverse of this gigantic matrix and multiplying it times R and solving for all the stresses in the part. So that's the process that the CAD system goes through. And the last step, according to the author, was we need to somehow interpret the results. And so most finite element systems today give us these nice pretty pictures. They give us a nice legend on the side. And they assume that you knew how to kind of give it the right problem. You knew how to give it the right boundary conditions. You knew how to give it the right loads. You knew where to apply the loads. So the rest of this period, we're going to take a few minutes and kind of talk about the CAD approach. So the author does, I think, a reasonable job with kind of doing the background and the mathematics, and I'm going to encourage you to read that. What we want to do is figure out how can we take this and apply it to our RC project that we're working on. Now, just a note about that. You have been doing topology optimization on some parts, right? So you take a part as a design space and non-design space and you load it, you do topology optimization, and it gives you this kind of ugly tessellated shape, and you take it into the CAD system, and what are you supposed to do? You're supposed to try and remodel it in the best shape that you can represent a manufacturable kind of shape. Is that effort on your part, is that an exact duplicate of the topology optimization? It's an approximation. Okay? You've had to make some kind of judgment. Well, I'm going to trim a little off of here because I don't think that looks quite right. I'm going to add a little material over here because I think it's going to look better if I add material. So you're making some adjustment to that design. If you were to use the topology optimization and just were able to do that, you shouldn't have to go and recheck the analysis. But because you're making some judgment,